So thank you for coming today. This is Annalie Peterson. She is born in St. Paul, Minnesota, shares maybe a same hometown as Dr. Bernie, raised in Minnesota. So she knows her rivalries quite well. Graduated in high school in 2018. I was trying to think back what I was doing in 2018, but then I gave up. And then, but because she's from St. Paul, she also had a spiritual connection with Dr. Bernie. She knew she wanted to go into geology, and so verbatim here, this is verbatim. And that's how she ended up here. And so she decided on a minor in soils. And to give you a little bit of background, she was in my class in 2021, maybe. One of the only undergraduate students that interacted. And so she came up and asked questions. She was very insightful about things, wanted to know more about no-tillage. Didn't know much about no-tillage and agriculture, but she was trying. And so, but we saw great potential in Annalie. And so we asked her to be a part of a 4+1 program. And that was an honors program. She had high grades already. And so we asked her to join us. So she did part of her master's research that summer, and then she graduated that fall. And she had already by that time, she had 9 credits of soils under her belt for her graduate degree and 9 credits of soils then for her geoscience degree. And so she was able to use those for both. So a year later, she graduated with her undergrad December of 2021. And we are here today to listen to her speak about her master's research in 2022, which is quite an accomplishment. So the other things that are notable, that she's very close with her grandpa who lives in Lawler, Minnesota. And she likes camping and other outdoors stuff. Yeah, it was right here though. And then I'm not sure what else to add. So I added some other stuff for you for that. So yeah, you bet. So we're gonna let Annalie mic up.
That?
Sure.
Okay.
Anywhere in your.
On my person?
Sure.
I think that works. Okay. Do I start now? So the title of my talk is Calcium acetate, an alternative to gypsum for improving oil field brine impacted soils. And so to start this conversation, I want to start off with some background information about oil production in North Dakota. And so this graph shows oil production in the state over about the last 40 years. And then as you can see, since just before 2010, there was a massive increase in oil production in the state. And as of 2022, North Dakota was ranked as being the 3rd largest producer of oil and gas in the United States, 3rd to Texas and now New Mexico. And so this next image shows a map of North Dakota with the Bakken and Three Forks formations outlined by the brown units. And those currently are the rock units that hold most of the oil and natural gas that North Dakota produces. And the points on the map represent wells that have been drilled from 2007 to 2018. And so the reason for this massive increase in oil production around the 2007, 2008, 2009, 2010 timeframe is because of advances in unconventional drilling. And so historically, North Dakota used to use conventional drilling techniques, which involves drilling vertically down into a larger reservoir in oil and gas. And usually these larger reservoirs are found at like the apex of an anticline, for example. But in 2008, North Dakota started to adopt some unconventional drilling methods. So that involves drilling downward to a kickoff point where drilling then continues laterally through the oil and gas filled shale in this schematic. And so then once drilling is completed, then fracking and pumping of oil can then commence. And so this next image shows the Williston Basin in North Dakota. And so the left side of this image represents the border between North Dakota and Montana. And then the right side of this image represents the border between North Dakota and Minnesota. And the Williston Basin is a really unique geologic structure because it's one of the only places worldwide that has like this complete package of sediments. There's only 4 disconformities that represent lapses in geologic time in the Williston Basin. And a lot of the sediments in the Williston Basin are marine with a few terrestrial sediments as well. Some of those marine sediments include the Madison Group. And so this was the main rock formation that North Dakota used to use for most of its oil and gas exploration using conventional drilling techniques. But once those advances in unconventional oil exploration started to be adopted, then we could start exploring the Bakken and Three Forks formation. And so this image is drawn to scale, but even though the Bakken and Three Forks is a lot smaller than the Madison Group, the reservoirs found in this rock unit still far surpass those found in the Madison Group. And so I want to talk a little bit about why we see a lot of these marine sediments in the Williston Basin, including the Bakken and Three Forks. And so these two rock units were deposited between the late Devonian and early Mississippian periods. And also during that time, the Kaskaskia transgression was occurring, and that's one of 6 major high sea level events that's recorded in Earth's history. So during these high sea level events, that represents all-time high sea level events. And so marine waters began to inundate continental interiors, and a lot of these events are distinctly marked with large packages of sediments being deposited. And so I wanted to show this image. This is Earth 359 million years ago, and this is right at that border between the late Devonian and early Mississippian periods. And so if you look at panel B, which is blown up, that's what the United States will be. And I've put a box around North Dakota, and you can see at this time, most of the state was covered by shallow marine seas. And so this means that we're getting deposition of marine sediments. And with this deposition of sediments, we also get an accumulation of organic matter, which then leads to the formation of the oil and gas that we produce in the state. And also as sedimentation occurs, the water in these sediments is squeezed out, leaving the salts behind. And so then that leads to the byproduct of brine, which we produce alongside of our oil and natural gas. And so brine is primarily composed of sodium chloride. This is an example of what a brine solution looks like from the Williston Basin. Makes sense since it's our ancient seawater that it would be composed of sodium chloride. And then the electrical conductivity of our brine solutions often exceed 200 decisiemens per meter, and total dissolved solid measurements are also often greater than 250,000 milligrams per liter. Can I do that? I'll just do that. Okay, and the amount of brine that we produce from our wells kind of varies through time. Typically with our younger wells that are newly drilled, we see about a 2-to-1 ratio of oil to brine that's produced, up to about a 4-to-1 ratio of oil to brine that's produced. But then through time, this ratio kind of begins to shift until sometimes we see about a 1-to-2 ratio of oil to brine that's produced in the Williston Basin. And sometimes in extreme cases, we can even see a 1-to-100 ratio of oil to brine that's produced. And so this next image shows a map of North Dakota, Montana, and South Dakota. And the red line represents the Bakken formation, and the points on the map represent samples of brine that were taken. And the color of these points corresponds to the amount of total dissolved solids on these samples. And so it's a little bit hard to see here, so I blew it up a little bit. You can see that there's a lot of variability of these points, but I think it's also obvious to see that there's a lot of red points on this map, which represent samples that have greater than 321,000 milligrams per liter of total dissolved solids. And so why are we so concerned about brine? Well, brine, when accidentally spilled across a landscape or when it's leaked from a pipeline, etc., can have really detrimental effects on a landscape. And this is an example of what that might look like. And so I'm particularly concerned with how brine affects our soil structure. And so what it looks like to have an unimpacted soil can look like this first part of the schematic. And so we see that our soils are aggregated, and there's macropore space that allows our water to move through those soils easily. Whereas if we have a brine impacted soil, these soils might begin to swell, and this kind of stops any water movement that we might see until eventually, in some cases, we can see soil dispersion. This basically eliminates any water movement through our soils, destroys the soil structure, and it's the sodium from the brine that causes this dispersion. But it's important to remember that it's not just the sodium from the brine that causes dispersion. It's actually the relationship between the sodium adsorption ratio and the electrical conductivity that decides if our soils are going to disperse or not. And so if we have a high SAR and a high EC, we'll likely see stable soil structure. Whereas if we have a high SAR and a low EC, we'll likely see some structural problems like dispersion. And so what it looks like to have sodium on our soil exchange sites versus another cation such as calcium is shown in these two schematics. And so sodium can lead to dispersion, whereas calcium is known as a cation that promotes soil flocculation. And there are a few reasons that we see this. Essentially, all of these reasons come down to their charge density. And so sodium has a low charge density compared to calcium, which has a 2 times higher charge density. And so both of these cations have a relatively similar ionic radius, but calcium has a +2 charge compared to sodium with a +1 charge, leading to calcium having a 2 times higher charge density. Also, sodium has a certain affinity to be hydrated, whereas calcium does not. Again, this kind of comes down to the charge density. So calcium tends to hang on to its electron shells more tightly, doesn't allow water to inundate those shells as readily as sodium does, which can lead to swelling and dispersion. And then the third reason that sodium has the potential of causing swelling and dispersion is because it's less coordinated on soil exchange sites. So it holds those clay particles less tightly together compared to calcium. And so we know in order to prevent dispersion, we want to remove sodium and replace it with cations such as calcium. And historically, gypsum has been the most common in situ amendment that's been used for sodic and brine impacted soils. And this image shows what that can look like. And so there's 2 brine impacted soil aggregates. One of them is put into a petri dish with water, and then one of them is put into a petri dish with calcium sulfate. And so we can see that there is greatly improved aggregate stability. And so some examples of gypsum that we have in our lab are shown here. These are some pelletized forms. And so some of the pros with gypsum is that it's really easy to find. You can find it at any garden store. It's also relatively inexpensive. But some of the drawbacks with gypsum is that it's relatively insoluble. And in order for our amendments to be an effective solution for improving our brine impacted soils, they need to go into solution to allow our cations to interact with each other. And also with these garden store options, they're usually in that pelletized form, and so they have a really low surface area, leading to a lower reactivity. And another type of gypsum I want to talk about is flue gas desulfurization gypsum. And so during coal refinery processes, coal is heated and this emits SO2 gas. And to prevent SO2 gas emissions into our atmosphere, those emissions are instead redirected through wet scrubbers. And once these gases are in wet scrubbers, they are sprayed with calcium carbonate slurry or a solution. And this reacts to form calcium sulfide. And so at this point, the calcium sulfide is a waste product. And so some facilities choose to force oxidate it to calcium sulfate, which is then our synthetic gypsum or our flue gas gypsum, which can then be used for agricultural purposes or for drywall and stuff like that. And so some of the pros with flue gas gypsum is that it's a powdered form, so it's a higher surface area than pelletized gypsum, leading to it having a higher reactivity. It's produced locally in North Dakota. It's also really inexpensive, but it still is gypsum, so the solubility is still a concern when using this amendment as well. And so with this in mind, you might think of other calcium sources that are more soluble, and an example of some of those might be calcium nitrate. And so calcium nitrate has a really high solubility and is actually an amendment that's currently used for brine impacted soils. But something to consider when you're using calcium nitrate is that North Dakota has the maximum contaminant level for nitrate nitrogen set at 10 parts per million. And another source of calcium that might come to mind is calcium chloride. And again, a really high solubility, but the maximum contaminant level of chlorides in North Dakota is 250 parts per million. And especially in these brine impacted areas, we already have loads of chloride in our system. So we don't want to dump more chloride salts in that impacted area. And so with the limitations of gypsum and other factors that we should take into consideration with our other calcium sources, this brought about the idea of using calcium acetate as an amendment for brine impacted soils. And so calcium acetate has relatively the same amount of calcium that gypsum does, but it's much more soluble. One drawback of calcium acetate is that it is a little bit more expensive, but really it's the solubility of our amendments that we need to take into consideration, especially in the western counties of North Dakota, where we produce most of our oil and natural gas. we see very little rainfall. And so even though calcium acetate is more expensive than gypsum, the idea is that less time and less water is needed for calcium acetate to be an effective amendment to introduce enough calcium to replace sodium in our brine impacted soils. And so this brings me to my investigative question. Can calcium acetate be used as an alternative to gypsum for improving brine impacted soils? And to answer this, I'll also be asking two other questions. Is calcium acetate more effective at increasing water flow? And is calcium acetate more effective at removing sodium? And so to begin investigating this, I used 3 soils. I named them accordingly to where they were collected. So one of them is from Bainville, Montana. The other 2 are from Williston, North Dakota, and then Glenburn, North Dakota. And I have listed the corresponding soil information with each of these soils, cation exchange capacity, the electrical conductivity, percent sodium, and the percent clay content. And these are the amendments that I used for this experiment. I had my calcium acetate, pelletized gypsum, and flue gas gypsum that were mixed with each of these soils at a variety of rates ranging from 0 megagrams per hectare up to 44.8 megagrams per hectare. And so once everything was mixed up, I then began my experiment. And so my experiment was measuring the saturated hydraulic conductivity, but for the rest of this talk, I'll just shorten it to KS, which I'll probably just call KSAT. And so my Tempe cells, which are shown on the bottom right here, were packed similar to those methods used by Sommerfeld et al. 1984. And so I incrementally added my soil to my Tempe cells, and I tapped the edge of the Tempe cell to allow the soil and their amendments to settle and compact. And then before adding the next layer, I would disturb the surface a little bit to prevent any artificial boundaries from forming in my Tempe cells. And so then once everything was assembled, they were randomized amongst the Tempe cell holder, which is shown in the upper right, and then connected to a Marriott bottle with a 20-centimeter head, which is shown in the lower left here. And so then my water would then move through my soils. I'd collect that either in beakers or centrifuge tubes and about 15 to 25 milliliter increments. And then with that, I could then determine the rate or the saturated hydraulic conductivity based on the time it took for a certain amount of water to move through my soil. And so for each of my soils, I had 3 treatments. They were applied at 4 different rates. And I did these each 4 times or 4 reps. And I also had 4 reps of a control. That means I had 52 total KSAT runs. So this brings me to my results, or a table of means. And so the different letters on or associated with these numbers represent significant differences that were identified using Fisher's least significant difference test at alpha equals 0.05. And so first I want to look at the effect of the soil on the KSAT and the residual sodium left in the soil. And so as you can see, there was an effect caused a different KSAT and different amounts of residual sodium to be left in each soil. And there was also a significant effect on the KSAT and residual sodium from the interaction between the soil and the amendment. Also, a significant effect from the soil and the rate. And so this was kind of unexpected, but when we look at the particle size and clay fraction of each soil, I think we can explain this a little bit better. And so each of these soils are a similar texture, either a loam or a sandy loam. But if we remember from the previous slide, looking at the KSAT, the Williston and Bainville soils were similar, whereas the Glenburn was different. And so even though these are all similar textured soils, when we look at the clay fraction, we can see that the Williston and the Bainville soils have a significantly higher smectite clay content compared to the illite content. Then looking at the Glenburn soil, we can see that there's much lower smectite content, much higher illite content. And so this difference in our clay mineralogy likely explains why we see those differences. And so now I want to talk about the effect of amendments. And so we can see, looking at the KSAT, the calcium acetate had the greatest effect at increasing KSAT, followed by flue gas gypsum, and then finally followed by pelletized gypsum. And then looking at the residual sodium, calcium acetate and flue gas gypsum had similar effects, whereas pelletized gypsum was least effective at removing sodium. And then I want to look at the rates. So in general, with increasing rates, we saw an increase in KSAT and a decrease in our sodium. And so also with that, the effect of the interaction between the amendment and the rate significantly affected the KSAT, meaning that with increasing rates of a certain amendment, we did see an increase in KSAT, whereas we didn't see an effect between the interaction of the amendment and the rate on the residual sodium. That was also slightly unexpected, but we'll look at a data set and that might explain why we didn't see that. And so we're going to look at my data set from the Williston soil, not at the Bainville or the Glenburn soil, because all of these trends are similar. And so just to save myself from repeating everything, I'm just going to look at this one data set. And so this graph is split into two panels. The upper panel is the graph for the KSAT. Y-axis is measured in centimeters per hour. Then the bottom panel represents the residual sodium, which was measured in centimoles of charge per kilogram. And then the x-axis for each of these panels is the rate of application of each amendment, which was measured in megagrams per hectare. And then again, the letters on each of these bars represent, or different letters represent significant differences that were identified by Fisher's LST test at alpha equals 0.05. And so when we look at the calcium acetate amendment, we can see that with increased rates of calcium acetate, we saw a continuous increase in our KSAT. And then with increasing rates of calcium acetate, we saw also a gradual decrease in our sodium, basically mirrors each other. And so next, looking at our flue gas gypsum, we saw kind of this gradual increase in water flow, whereas we saw a really abrupt decrease in our sodium, which might be why we don't see a direct effect on the residual sodium when we're looking at the interaction between the rate and the amendment. Then when we look at the pelletized gypsum, we can see that with increased rates, we see little to no increase in water flow, kind of this gradual decrease in sodium. And so just to recap, looking at each of our amendments and their effect on the soil, with increased rates of calcium acetate, we saw a really large increase in water flow. And with increased rates of our calcium acetate, we also saw a large decrease in our sodium. And with flue gas gypsum, with increased rates of that amendment, we saw kind of an intermediate increase in water flow. And with the lowest rates of our flue gas gypsum, we still saw the most significant decrease in sodium. And with increased rates of pelletized gypsum, we saw little to no increase in our water flow. And finally, with increased rates of pelletized gypsum, we saw kind of an intermediate decrease in our sodium. And so to conclude everything from those slides, calcium acetate was the most effective at improving brine impacted soils out of the three amendments, followed by flue gas gypsum, which had kind of an intermediate success at improving brine impacted soils, followed by pelletized gypsum, which was the least effective amendment in this experiment. And so this next slide shows where I would like to see this laboratory experiment go next, and that would be in the field. And so reading this from left to right, first we'd have a brine impacted area. This soil would likely have high SAR, high EC, and a lot of the times in these brine impacted areas, you'll see some salts accumulating at the surface and sparse vegetation. And so in that area, I would surface apply my calcium acetate and then irrigate, which would allow all my salts to solubilize. And at this point, it would be really important to keep in mind the relationship between the SAR and the EC to prevent dispersion. And so once everything is in solution, calcium is then able to replace sodium on soil exchange sites. This will decrease the SAR, reduce the risk of dispersion, and also increase the KSAT. And so once our calcium is on the exchange sites, we could collect the sodium and the chloride through something like tile drainage and then dispose of it safely through deep injection. Additionally, another avenue that this research could take would be investigating if the acetate could serve as an available carbon source for soil microbes, but during this study, that part was not adequately investigated. And so I was lucky enough to be invited out to parts of North Dakota to see my research in action. And so I've had a couple companies around North Dakota that have used my research so far. This is just an example of one of those opportunities that I was invited to be a part of. And so they had a calcium acetate source. In this case, is Calase 10, which is actually like an apple fertilizer. And so these are just some pictures of that opportunity I got to be a part of. A small brine impacted area. We were mixing all of our really concentrated fertilizer in those tanks. There was a water tank up there next to the well pad where brine leak occurred. And so in addition to my research, I was also able to write an extension publication, which has yet to come out, but keep your eyes out for that. And it's titled Origination of Produced Water in the Williston Basin. And so these are some of the images that I created for that, just to give you an idea of what that talks about. So we have talked about different sedimentation processes, the formation of oil and gas, different pumping and drilling techniques, and also different reservoirs that we see in the Williston Basin. And so with that, I'd like to say thanks to my committee members, Dr. DeSutter, Dr. Meehan, Dr. Day, Dr. Saniaticat, also to the technicians that helped me with this, Nate and Kevin. And I didn't expect my undergraduate bosses to be here, but I'd like to thank Dr. Lepper, Dr. Tackett too, and also to the North Dakota Department of Environmental Quality for funding this research. And thanks to all my friends who helped me along the way and who I met. And then these are some sources I used to put this talk together. And that concludes my talk about using calcium acetate as an alternative to gypsum for improving brine impacted soils. I'm going to leave off on this slide because I like it better. And with that, I'll take questions.
Do you have any questions for Annalie? I'm going to ask her to repeat the question.
Okay. Yes. Thank you.
I have two questions that are more on your stuff.
Sure.
So first of all, you kind of mentioned, I'll ask you both to kind of go together.
Okay.
You mentioned that typically this is brine impacted soils are because of like an accidental like spill or a leak. So I'm wondering if that's what's happening to the burn.
Sure.
And then my second question is, I guess, you put out the prices for these three products by ton, but I'm curious if that, like, how that applies to the actual, like, treated acreage cost, if that's similar.
Sure. Second question, maybe clarify a bit on that.
Okay. So you had like $1,000 a ton, $10 a ton, and $200 a ton?
Yeah.
Does that translate to like how much it would actually cost to apply and how much it is per acre?
Okay, I think I can answer that. So the first question is, what are we supposed to do with our brine? So a lot of the times the brine spills occur during like on-site desalting processes when we're separating the brine and the oil. Sometimes spills can occur there, or during transportation processes through like pipelines or trucks, but usually spills are supposed to happen through deep injection, and usually they put it back into the Dakota Formation, which is a Cretaceous shale, so it lies above those oil units in the Williston Basin. And then the second question was talking about the cost of the amendments and if that applies to actually the cost of the remediation. Is that okay? So I think that depends again. There's research that shows that gypsum is only effective to the depth at which you apply it. So I could imagine that when you're using like an amendment like gypsum, that there would be additional costs that you'd have to factor into that to like till it in or something, whereas calcium acetate might not have those same costs. I guess I can't like quantify exactly how much that would be, but those are other factors that I think would be important to consider. It. That answers your question, hopefully. Okay, sure.
I want to follow up with that.
Yeah.
So the way I would phrase it would be, can you normalize it to the amount of calcium ion released? That would, that might make the acetate cheaper if it's
Sure.
really soluble.
Yeah, you wouldn't have to use much. That makes sense. Nate?
Do you think in your chemical experiments that mineralogy, you're getting less KSAT because of it?
Sure. I think that was also, yeah, the clay mineralogy affecting my KSAT. I think there was that was probably a large component of that because my fastest KSAT was in my soil that had the least amount of smectite in it, which was that shrink swell clay. And also my higher smectite clay contents I found took longer to saturate. And so I think that also played a factor in that. That answers your question, hopefully. Sure.
Scott Stockdale had a question. What type of spacing and depth were you looking at for drain time?
Sure.
I think the question revolves around if you can have a recommendation.
Yeah.
What might,
I think sometimes that's hard when you're talking about like the spacing of drain tile, because sometimes the affected areas are really deep. But from talking to people that are actually putting in drain tile to recreate this experiment, they haven't hammered that down, but I've asked them what they kind of plan on doing. But I would say, like, obviously, depending on how deep it is, there's only so deep you can insert your drain tiles. But I would say probably more frequently than typical agricultural practices, but I can't say for certain. More frequently spaced, I should say. Yes.
I have another background question. And then, so
Okay.
you teach your old boss. I don't like to be thought of as the boss, but
Yeah.
always wondered that, I lived in Oklahoma for a while and they used tons of gypsum.
Yeah.
I've always wondered, can you get enough sulfate in the soil to also cause problems, or has anyone used?
I haven't looked into that, or if the effect of gypsum introducing too much sulfate to the system. I haven't looked into that too much. And when I talk to people about it that are in this field and use gypsum, I feel like they're more excited about introducing sulfate as like a micronutrient more than it being like a toxic factor. But I haven't seen literature that would indicate that it'd be bad.
The brine that's spilled, is there some incentive or problem with it being located deep in the soil? I mean, is it gonna affect the groundwater?
Yeah, sure. That's also, so the question was asking about the depth in which spills occur and if that affects any groundwater movement. So yeah, that's a really large issue, especially looking at, I don't know if I can say this, but looking at the 2015 Blacktail Creek spill, that has reached groundwater tables. And so there's a lot of monitoring that they currently do with really deep wells, and cleaning that up is a lot harder. I've seen people try to implement tiles to those depths of like 20, 30 feet, but obviously you can't install them like you would normal agricultural tiles. You have to bore them in. And I've seen that done to try and mitigate some spill sites, but yeah, it definitely complicates things, and groundwater safety is definitely a concern, especially with chlorides. Most people that are mitigating these spills aren't especially concerned with sodium, even though they should be. It's more the chlorides just to like maintain state regulations and stuff like that. But yeah, definitely complicates things.
the question online here, with the increased productive capacity, efficiency of capacity of calcium acetate treated soils also alleviates some of the increased expense. And so leading to a wider use of this product.
Maybe I need to read that one. I think that was what we had asked before, right?
Similarly.
So I guess I haven't looked into that, like looking into how much gypsum actually goes into solution, or like if you can apply less calcium acetate compared to gypsum to alleviate some of that cost. But I think it's definitely worthwhile to look into.
And certainly,
Okay.
we just have to remember that it's the time thing too, right? It's
Sure.
not just the initial cost. It's like if it takes 5 years versus takes 20 years or 10 years,
Yeah,
there's the landowner cost on top of it.
yeah.
Part of that question is also getting at that, can the ground actually be used to grow something?
That's what I was gonna say. I think the question more has to do with the capacity of the soils to produce product.
After amendment application, sure. Well, I think that's, yeah, of course, the overall goal is to displace the sodium, because it's not necessarily, I think it's the sodium that's like affecting this plant I don't know if that's the right word, physiology, where we get like this osmotic stress on our plants and also our soil microbes. And so there's that detrimental effect from brine. Then there's also the physical and chemical effects that brine can have on soil. So it's all of these factors that kind of make an ecosystem uninhabitable. And so whatever amendment you're applying, if you're able to remove the sodium, I think is going to repair that ecosystem, whether it be calcium acetate or gypsum. So of course, I think the goal is to remove sodium for many reasons to make the land usable again, because that's kind of the overall goal of reclamation, right? It's just. So I think application processes, in my mind, when I'm thinking about where I would like to take this, I would assume that application processes would be easier with calcium acetate since it is so soluble. I think that you would be able to surface apply it compared to gypsum. There's been numerous studies that show that you have to incorporate gypsum. And so then you would eliminate some of those costs with that. Although some of the companies that have adopted this research have been mixing their calcium acetate in just because the sites have already been excavated and they're backfilling with contaminated material. And so I don't think they're mixing it in because they think they have to or whatever. I just think it's because it's feasible at that point. They've already excavated, they're backfilling, but it would be interesting to, you know, see if you could eliminate those costs by just surface applying.
Scroll up one.
Sure. I think that's similar to what I've also investigated or been a part of is you install tile drainage and pump your calcium acetate solution directly into those tiles and then collect it through a series of tiles that are located below that. I think that can definitely be a feasible option. It's really interesting to see that done. Yeah, I think it could be something that would be effective maybe on smaller plots. And then, sure. Yeah, so I know that in general, soil washing, you probably get the removal of other nutrients. But in the study, I didn't look closely at other nutrients or other salts. Really just looked at calcium and sodium, whether one increased or decreased. And I guess that's the best I can answer that one, because I just didn't look into that one too close.
So if in a general sense, though, the soil fertility that is there
Probably decreased.
decreased.
Yeah.
So.
Yeah.
In a cropland setting versus rangeland setting, obviously there's going to be differences with what is required.
Yeah.
Could one add essential nutrients back in either setting?
I would, sure. I mean, as long as, you know, you're removing all of your harmful constituents, then I think you can kind of just start over from point zero. The whole reclamation process would look like recropping, and that would also involve applying fertilizers and such. So, but yeah, I mean, when you're talking about literature and like soil washing and replacing sodium with other cations, there are other literature that looks at like macro and micronutrients and how they are flushed out through time. And in general, like all of those nutrients are flushed out. So yeah, I think replacing those is probably vital for overall reclamation. But yeah, just in this particular study, we didn't choose to measure those, but I have read other papers that look into that.
And final questions? Question? Okay, Annalie, well, thank you very much.
Oh, thanks.
So as in, we have a parting gift.
Oh my,
So these are,
it's like a repeat of yesterday.
yeah, I think you might have seen these yesterday.
Yeah.
This is a pair of socks that is a soil profile on them, and there is some geology on the bottom there. So.
Oh, thanks for the socks. Did you get these at the conference?
I did.
Oh. Fun.